Hello and welcome. In this video I'll be covering section 2.6, which is over higher order derivatives. My goal for you by the end of the video is to be able to find higher order derivatives, as well as to be able to find and use the position functions to determine the velocity and acceleration of moving objects. So what are higher order derivatives? Well, the derivative of f prime is what we would call the second derivative of f and is denoted by f double prime. And then the derivative of f double prime would be what we would call the third derivative of f, and it would be denoted by f triple prime. And continuing this process, we obtain what we would call the higher order derivatives of that function f. So as far as notation is concerned, in your book you can see this table, but I'll just kind of sum up everything that's in this. So the notation here, as you can see, the first derivative we've already talked about, something that has a single prime, so like y prime or f prime, or in other notations you could say it's dy over dx or d over dx of f of x, or even the d sub x of y. So as you can see, as we go, the second derivative and third derivative and fourth derivative and so on and so forth, we just add extra prime symbols. So like for the second derivative it would become y double prime, for the third derivative it would be y triple prime, and once we get past that to a certain point, we get to, I guess, where there would be too many prime symbols really to be able to want to count it. What we do to denote it is actually just throw a number in a parenthesis to kind of specify that this is a derivative, not a power. And so if I needed to do, say, notation for like the eighth derivative, I would just say something like y and have parentheses 8 as kind of a superscript for that particular thing. So again, just kind of take note of the how derivatives can be, I guess, written or notated from this slide right here. Alright, so let's go ahead and work through a few examples. This one, notice it just says to find the first 5 derivatives of this function. So we have our original provided for us. So if I wanted to find f prime of x, I would just take the first derivative of it. So with this one, the power rule would be what we would employ. So the 4 would come out, multiply with the 4 in front, so that would become 16x cubed minus, and then again power rule, so 2 would multiply with the negative 5 to turn into negative 10, and then drop by 1, so just x. To come up with the second derivative, I just now take the derivative of my first derivative, so now it would be 3 multiplying with the 16 to turn into 48x squared, and then minus the derivative of 10x would just become 10. Go on to third derivative. Third derivative of this one, I would have 2 multiply with the 48, which would turn into a 96, and then drop by 1, so just x, and then the derivative of the constant 10 would turn into 0. If I go to f, I guess, the fourth derivative, so I'll go ahead and denote this a little bit different. F of 4 of x would equal just 96 for this one, and the fifth derivative would now just be, since that's a constant, it would just turn into 0. So notice, doing higher order derivatives, we just continue taking derivatives of the previous expression. Go through another example here, a little bit different instructions. Now I actually want to find the value of a specific derivative. So in this case it says to find g triple prime, or the third derivative of g, at this value 1. So I would just start with finding what my first derivative is. So g of x, or g prime of x, would equal, looks like for this one, 4x cubed minus 3x squared, then plus 2. G double prime, or the second derivative, would turn into what looks like 12x squared minus 6x, and then plus 0 at the end. And now find my third derivative, so g triple prime equals, in this case, 24x minus 6. So now it wants us to find a specific value for this, so I would now, to find g triple prime of 1, I would just plug 1 in, so it would be 24 times 1, then take away 6, so that would really just be a 24 minus 6, which would turn into 18. So the value of this specific function at its third derivative at 1 would be this value 18. Yet another example here. We'll go ahead and find the first 4 derivatives of this function. So this one, notice, is a rational function. First thing I would do with this one is go ahead and rewrite the x using a negative exponent. So this really would be x to the negative 1. So to find my first derivative, f prime of x, that would turn into negative 1 coming out front, and then drop by 1, so x to the negative 2, which really would be able to be simplified to be a negative 1 over x squared. However, with this, for the second derivative, I actually want to utilize the one that had the negative exponent, so I can continue using the power rule. So with this one, it would turn into negative 2 times negative 1, which would be positive 2, and then drop by 1, so x to the negative 3, and then rewrite, so that would become 2 over x cubed. If I wanted to go to the third derivative, again, I would use the one that has the negative exponent, so negative 3 multiplying with 2, that would be negative 6, and then drops by 1, so x to the negative 4, which again I could rewrite and call that negative 6 over x to the 4th. And we'll go ahead and do our last one here for this problem. The fourth derivative of f would turn into negative 4 times negative 6, so positive 24 x to the negative 5, which, getting rid of the negative exponent, just drop it to the bottom, and I would get 24 over x to the 5th. Do another little bit more complex derivative here, or third derivative. Notice this one now we have a product to begin, as well as a function inside of a function, so I have a little bit of a chain rule. So this is going to require both a product rule and a chain rule. So to come up with our first derivative, we would take advantage of those two processes. So it's going to be keep the first, so 2x times, and then the derivative of the second. So start with the derivative of the outside function, which would be like x cubed in this case, so 3 would come out front. 3x plus 1 quantity squared would be inside, then times the derivative of the inside, which is in fact 3. Then add that with the derivative of the first function, so in this case that would just be the derivative of 2x, which is 2, and then times, and then we'll keep the original second function. So with this one, best thing to do from here is go ahead and look at, is there any way that I can simplify what we have? Looks like they both have a 2, so I could factor 2 out, and they do both have a 3x plus 1. In fact, they actually have 3x plus 1 squared in common, so I could factor that out. And then what's that leave for each term? Well, it looks like to me on this first one I've got 3 times 3, which would be 9, still times x, so 9x, and then plus the second one, the 2 would be gone, and 2 of the 3x plus 1s would be gone, so that would just leave a single 3x plus 1. So if I look at what that would be able to simplify to, I could say that this is really 2 times 3x plus 1 squared, and then 9x plus 3x, that's really 12x plus 1. So there's my first derivative. If I move on to finding the second derivative, again I have a product rule going on. The coefficient of 2, I could just say, is going to kind of separate itself, kind of take advantage of that property, and we'll go ahead and just start doing our product rule again. So I've got 3x plus 1 squared, then times the derivative of the second function, which is just 12, then add that with, I'll keep the second function the same, so 12x plus 1, but then times the derivative of this first part, which again is a chain rule, so 2 would come out front. I'd have 3x plus 1, and then the power on that now would be 1, but then times the derivative of the inside function, which is 3. Make sure I closed off all of my parentheses that I needed to. So now if we look at what we have, we can go ahead and again see if there's anything we could factor out. So it looks like I've got a 6 and a 12, so I could take a 6 out and multiply with the 2 that's in front, so that would turn into a 12 outside. And it looks like I could also take out a single 3x plus 1, because there is at least that in common between the two terms. And then now let's write what's left. So in this first one, it looks like I've got a single 3x plus 1, but then if I only took 6 out of the 12, that would leave 2, so I really have 2 of those 3x plus 1s. Then added with, looks like the only thing that would be left from the second term is just that 12x plus 1. So if I try and simplify this a little bit further, it looks like I've got 12 multiplying with 3x plus 1. And then that would be multiplying with, if I distribute this through, I'd have 6x plus 12x, so that would be a total of 18x. And then I've got, looks like 2 plus 1, so plus 3. And with that one, it looks like I could probably factor out a 3 from that as well, so I may as well take the 3 out, multiply it with the 12 in front, so I've got 36 times, and then I've still got the 3x plus 1. And then if I did take the 3 out of that second parenthesis, it looks like that would turn into 6x plus 1. And so now I've kind of run out of room, so I'll just kind of move these things up into this area for my third one. So my third derivative for this one, since that's what the question was requiring us to find, would be to go ahead and keep that 36 in front. And now do a product rule again, so keep the first, 3x plus 1, times the derivative of the second, which is just 6. Then add that with, keep the second, 6x plus 1, times the derivative of the first, which would just be 3. And again, I'll just go through my simplifying process. Looks like I could factor a 3 out of those two, because I have a 3 and a 6, so 3 coming out front would turn that 36 into 108. And so that would really turn that 6 into a 2, and that 3 would be gone over here. So distribute that through, it'd have 6x plus 2, then plus a 6x plus 1. So I could simplify that and say this is really 108 times 6 plus 6 is 12x, and 2 plus 1 would be 3. So once again, it looks like I could factor a 3 out just to simplify or lessen some of those numbers. So if I go ahead and pull 3 out, multiply it with the 108, that would turn into a 324. And 3 out of 12 would leave 4x, and 3 out of itself would leave a 1. So there is my third derivative for that specific function. So what are the applications of these higher order derivatives? Well, one of the possible applications here would be for like the vertical position of a falling object, or just a object that's traveling on a perfectly vertical line. Remember, it was denoted by this p of t equaling negative 16t squared plus v sub 0 times t plus h sub 0, where again the v sub 0 was the initial velocity and the h sub 0 was the initial height. So the first derivative of that position function is actually what we could call the velocity function. And if you think about y, remember derivatives represent the slope, or another way we can denote that is the rate of change. So the rate at which your position is changing is something that we would call its velocity. If we continue further and take a second derivative, that actually turns into the rate at which your velocity is changing, which we have a concept called acceleration as the word that we could say that would represent. So let's go ahead and try out an example with this one. If I had a ball propelled straight upward from the ground level, so that would mean my initial height is equal to 0, with an initial velocity of 160 feet per second, so that would be my v sub 0, or my initial velocity. I need to find the position, velocity, and the acceleration function. So let's go ahead and knock that part out first. So my position function would be negative 16t squared plus 160t, and I know that's positive because it's going upward, and then plus the initial height, which is 0, so I could just leave the plus 0 off. So my velocity function here, v of t, would be the derivative of that, which would turn into negative 32t plus 160. And then my acceleration function is going to be the derivative of my velocity, which would just turn into negative 32. So now the follow-up questions here are, how high will the ball go? So the how high it will go, we could figure out when the velocity actually stops and starts coming backward. So that would really be, when does the v of t equal 0? So if I solve that, I'd have negative 32t plus 160 equaling 0. So first I would want to take the 160 over to the other side. I could have also just added the 32t over to the other side. That would have kept me with some positive values, but it won't matter because the next step I'm going to divide by a negative. So now if I figure out what negative 160 divided by negative 32 is, looks like my t for this one is 5. So it says, how high will the ball go? Would be when the velocity has become 0, which I just found was at a time of 5 seconds. So the how high it actually went would be its position at 5 seconds. And so I just plug 5 into that. So 16 times 5 squared, then plus 160 times 5. So let's go ahead and figure out what that value would be. So that would really be a negative 16 times a 25. Then added with 160 times 5, and that comes out as a value of 400 feet. So it would go a total height of 400 feet in the air. Then the second part is, how fast will it be traveling when it hits the ground? So its position when it's on the ground would be 0, so that would be take the position function, negative 16t squared. I guess I'll do that side work off to this area over here. So I've got negative 16t squared plus 160t. Figure out when its position is 0. So with this one, it looks like I actually can factor out 16. So I could say that this really is, actually I could factor out a negative 16. So let's go ahead and take that as well as a t. That would leave me with t minus 10. So it looks like my two places where it would be on the ground would be when I started, which makes sense because the question said it starts at ground level, but then also at 10 seconds. So as far as the what is the speed or how fast is the ball traveling when it hits the ground, that's just going to be what is the velocity when it's 10 seconds. So if I do negative 32 times 10 plus 160, that would really give me a negative 320 plus 160, which is a negative 160 in feet per second. If I needed to figure out its acceleration at any point, notice the acceleration function was essentially just a constant negative 32 feet per second, so feet per second squared. So at any moment, it technically is accelerating in a, I guess it's decelerating if you want to think of it that way, because that came back negative, it's slowing down, or the velocity is slowing down at a constant rate. So the pull of gravity in this case essentially would be negative 32 feet per second. So hopefully this video has been helpful in just finding these higher order derivatives, and we see a little bit of an application with the position, velocity, and acceleration functions. But as always, if you have questions, feel free to reach out and let me know. I'll do my best I can to be able to answer and get you unstuck if you happen to be stuck. I appreciate you taking the time watching the video, and we'll catch you next time.